Welcome back. So today we're going to continue with the macrominerals section. Specifically, we're going to do all the electrolytes, so sodium, potassium, and chloride. All right, so just starting with sodium. The body contains about 30 grams of sodium, so much less than the other macrominerals. And then do you remember how we distinguish macro from micro? Just take a second and see if you remember that. So if you remember, that's in the calcium lecture, and it's based on intake. So anything over 100 milligrams per day, intake-wise, is a macromineral. And then anything below that is a micromineral, so less than 100 milligrams per day. So yeah, sodium, potassium, and chloride are all macrominerals because we take in more than 100. So yeah, where do we find sodium? Surface of bone, some of it is found there, but mainly we're going to talk about sodium's function in fluid balance. So it's a major component of the extracellular fluid and soft tissue. So just remember probably from like even high school biology that, it's found on the outside of the cells. So the ECF, or extracellular fluid, and that's about 70% of body sodium is found kind of just in the fluid or outside the cells. In terms of food sources, basically you probably knew this before even taking the class, but a lot of our sodium intake is really from like processed foods and then just adding table salt to foods as we're like either cooking or, just sitting at the dinner table, whatever, and sprinkling some salt on there. There has been some changes in sodium and potassium DRIs, so I'll go over those. But just to let you know, right now the AI for sodium is still 1,500 milligrams per day. So you can write that on here. So yeah, 1,500 milligrams per day for both men and women. That's what the AI is. So if you want to compare to the 1,500, you'll see, just in one package of like ramen noodles, that kind of thing, you're getting pretty much all your sodium for the day. Scary thing for me, or people, I don't know, definitely if you like to go and eat sushi or cook with a lot of soy sauce or anything like that, just 1 tablespoon of soy sauce has 1,000 milligrams, which kind of freaked me out because, yeah, definitely I kind of go to town on the soy sauce if I'm eating sushi, just like pouring it in that little bowl. So I must be consuming like 4,000 to 5,000 or something milligrams. Definitely a few tablespoons worth. Other things is like potato chips, anything processed has higher amounts of it. And then if you're interested, I say down here, one teaspoon of table salt is 2,300 milligrams. I don't think anyone's going to add a whole teaspoon to a serving of food, but if you're interested, that's how much sodium is in that. But yeah, processed foods are definitely really high in sodium, whereas kind of naturally occurring things do contain like fresh fruits and vegetables, milk, all this stuff. Most of it does contain small amounts of sodium, but it's pretty small. Definitely when you start processing it, that's when the sodium intake increases. And I'll show you that in a couple slides. So in terms of kind of where we're getting sodium in our diets, a lot of it really comes again from like eating out, like restaurant foods, processed foods, that type of thing. There's been studies to show that about 3/4 of our salt intake is from processed foods and basically restaurant foods. Other things to point out on this graph, only about 12% of the sodium we eat is naturally occurring. So that means the stuff that was just in the foods just naturally. So the amount of sodium you're getting in that banana or that cup of milk or something. So very little, we would have very low salt intakes basically if we didn't eat a lot of processed foods. To explain, while eating means basically adding salt, like with a salt shaker while you're eating, so a little additional salt. And then home cooking is when you have, obviously the most basic ingredients like vegetables, and then you sprinkle some salt on there while you're like cooking them. So this is what I was going to mention with how processing foods changes the sodium content. So just to explain this first, this top row here is a whole bunch of kind of just like naturally occurring foods. So you have like milk or just normal corn or just a fresh peach. So kind of like plucking stuff right out of the environment or right out of the ground. That's what they're showing up here. Down here is the processed versions of those foods. So you take your corn, you make it into like cream corn. You take your peach, you make it into like a peach pie or something processed basically. So the naturally occurring ones and then the processed ones are here. And then the other thing to pay attention to is these ratios here. So pink is potassium, yellow is sodium. And so the main thing this kind of figure is trying to show you is that when you have the natural occurring types of foods like milk and stuff, you actually have really small amounts of sodium. So remember, sodium's yellow. Lots of potassium, little sodium. So the ratio of potassium to sodium is there's tons more potassium than sodium in a naturally occurring food. Then all of a sudden you take these things, you take your peaches, you make it into some kind of like pie or something, and then the ratio of potassium to sodium changes drastically. All of a sudden you have tons and tons of sodium in there. And then remember, this is a ratio, so it's not like you're getting rid of the potassium. I guess you probably have some, like maybe less peaches or I don't know. But in general, you're not like getting rid of the potassium. It's just the ratio is changing. You're adding so much salt that the ratio of potassium to sodium becomes pretty extreme. So generally, yeah, if you're a type of person that consumes very little processed foods, you're probably getting kind of lower intakes of sodium, which is great, and really high intakes of potassium, which is what you want to strive for. Just to go into a little bit about food labeling of salt, it's pretty confusing. I find it really hard to memorize these things. There's so many different labels for this, but once you know it, it might help you read, this stuff is labeled, like I show here, like ketchup and whatever, like bouillon cubes and stuff like that. But so salt-free means less than 5 milligrams per serving. So interestingly, salt-free, you're actually still getting salt in there. Very low is less than 35 milligrams per serving. And then low is less than 140 milligrams per serving. So whenever you see, again, labels on ketchup and stuff like that, this is what they mean. But I doubt any of the public actually knows what these numbers are. I don't think these numbers even appear on the packages. You're just supposed to know that very low means less than 35 milligrams somehow. Things that I see more commonly, though, rather than the like low, is more of this, like reduced and light. So reduced means that you take your ketchup and now you basically take out 25% of the salt. And so that's the reduced, like Heinz ketchup. So compared to the original ketchup, they now offer like reduced sodium. So that means it's 25 less than what was originally in there. Same with like light. You might see this on like potato chips and stuff like that. So compared to like Lay's original potato chips, the light version has 50%. But interestingly, light actually has more reduction than reduced. So I don't know. These words are all kind of confusing. So it is really hard to remember. Daily values are kind of one of the most egregious things that I've ever seen in nutrition labeling. But hold on, let me explain that a bit more. So if you remember what I said, the DRIs, so the AI for sodium is 1,500 milligrams per day for men and women. However, somehow the food companies, I guess, lobbied the FDA or the USDA, or the people that like control food labeling, and they said, you know what? We know that the AIs are 1,500 milligrams, but we think that on food labels, we should set a new type of value called the daily value. And let's just set it a little higher at like 2,400 milligrams. And the reason that they did that is because then it makes their sodium content of foods look a lot lower because you have to express it as a percentage. So here, if you had, 470 milligrams of sodium divided by the real 1,500 milligrams, which is the AI, that would be almost a third of your sodium needs, right? But now, because they got to create this artificially high daily value of sodium, which is 2,400 milligrams, now they get to show that their product has even less salt. So it's super confusing. It's definitely something that you should point out to your clients. So their real sodium intake that they should be striving for is 1,500, not the 2,400 milligrams. So I usually tell people just ignore these like percentages. So focus on the milligrams. Try to not go over 1,500 milligrams per day. So this kind of brings us into another important point with salt. And the main thing that you've probably heard about salt affecting is blood pressure. So a lot of people are really worried that, you know, if I have really high salt intakes, I'm going to increase my blood pressure. Interestingly, that doesn't actually happen in most people. So we found out that it's only about 20% of Americans that are salt sensitive. So those are people that basically have an increase in blood pressure if they consume high amounts of salt. So really only 1 in 5 people are affected by this. So only 1 in 5 people are salt sensitive. So again, you know, 80% of the population can pretty much consume as much salt as they want, and that won't affect their blood pressure. So yeah, that's kind of shocking if you haven't heard that before, because we kind of were taught, you know, kind of unanimously that salt's super bad for you, and the more you take in, your blood pressure is going to like shoot up or something. So the way that they test blood pressure or salt sensitivity and blood pressure is generally in like clinics. So dietitians can do it, doctors do it. But if somebody is diagnosed with high blood pressure, what they do is they put people on these like different like salt regimens basically. So first they start you off at this really kind of high salt intake, probably similar to what Americans consume, which I'll show you in a second, is around like anywhere from like 2,000 to 4,000 milligrams per day. And then every few days they lower the sodium intake, and then they're constantly measuring your blood pressure. So they start you off at a high intake of salt, measure your blood pressure. 3 days later, it reduces by, let's say, 500 milligrams, I think. They measure your blood pressure again. Then they keep on reducing the salt, and then they keep on measuring your blood pressure over the course of a few weeks. And then they just want to see, well, if we're taking all this sodium out of your diet, is your blood pressure going to go down? And so if it does, then you're a salt sensitive individual. But if they take all that salt out of your diet and your blood pressure stays just as high as it was, then you're not. So that's how they test that out. So the AI, just going back, remember it is an AI, it's not an RDA, and it's 1,500 for men and women. The reason that the RDA has not been set is because the link between sodium and hypertension is still pretty unclear. We know that whole thing about like salt sensitive individuals, but the whole mechanistic link between it is honestly not very well researched. So they're kind of hesitant to set a true RDA yet. And so, yeah, the reason that this was generally set is just because it's an effective level for maintaining plasma levels and maintaining like key functions of sodium. But as I mentioned before, most of us are actually consuming about twice as much as we need. So if you look at it, this is average sodium intake by ethnic breakdown. So remember, we're supposed to be at 1,500. So, oh wow. It's actually, I didn't even realize it didn't start at 0 here. So way below here, basically. So 1,500. So a lot of people are consuming anywhere from 3, maybe even up to like 4,000. So at least 2-3 times the amount of salt we should take in. American Indian and Alaskan natives consume a lot of salt because they use it to preserve like meats and stuff like that in like more Arctic environments. So that's why theirs is particularly high. But the rest of the groups are fairly similar. But yeah, between like 3,000 to 3,500 is typically what we consume. So about 2,000 milligrams more than what we're supposed to be eating per day. In terms of absorption, it's basically sodium's absorbed by 3 main processes. The first one's a glucose cotransport system. The second one's an electroneutral system. And then the last one's an electrogenic system. So it doesn't really fall into kind of what we saw for calcium, phosphorus, and magnesium, where they had very similar kinds of things as water-soluble vitamins, like the high and low energy dependent. Sodium's a little different. So the first one, just to go in a bit more detail, sodium glucose cotransport system. This is where basically a brush border transporter carries sodium and glucose together into the enterocyte, kind of at the same time. So basically you need glucose there, and then they both enter together. It's basically by this carrier. And then in order for sodium to leave the cell, this is done by a sodium potassium ATPase pump. And then that pump works by basically pumping out one sodium, so that goes out, in exchange for one potassium going into the cell. So that's how sodium gets out of the enterocyte. The second absorption mechanism for sodium is electroneutral sodium and chloride cotransport system. So this is kind of interesting. It's basically sodium uptake is increased in the presence of chloride. They're not quite sure why this is. And so what's happening is there's basically this pump. It's an antiport system where one sodium leaves for one hydrogen coming in. And this system tends to be kind of accelerated or upregulated when there's more chloride present. And then because there's more chloride present, chloride also enters the cell in exchange for one bicarbonate leaving. So it's basically, this mechanism is just when sodium and chloride are present in high concentrations together along the brush border, these are activated and both of them basically enter. And then they both leave with that, chloride just diffuses out of the cell, but sodium always leaves by that same sodium potassium ATPase pump, where again one sodium's leaving and then one potassium's entering. And then the very last one is basically just a sodium channel, where it basically just goes in based on a downward concentration gradient of the ion. So kind of the simplest one, it's just basically entering via a channel. And then always remember, super important, water always follows sodium. It's going to be in our water lecture, the next lecture we're doing, that's going to be a really key concept to remember. All of our blood pressure is regulated by water following sodium. So in this mechanism, this is kind of where the water is following the sodium. So what does sodium do? You probably do all this before taking the class. Just in general, you know that it's an electrolyte, so maintenance of fluid balance. You know about action potentials, so nerve transmission is a key one, and then muscle contraction too, because of that role with action potentials. So maintenance of fluid balance, pretty simple. Again, we're going to talk about this a lot more, like actual fluid balance in the water lecture, next lecture. But some basics. Remember again, sodium is the principal ion in the ECF, so that is extracellular fluid. It's on the outside of cells. So it's always, this is the outside of the cell here. It's usually in much higher concentrations on the outside. It's very little on the inside. So again, water follows sodium. That makes it a key determinant of blood volume and blood pressure. And then, yeah, just keep in mind that in order to raise your blood pressure or lower it, you're just moving sodium around. All right, so again, we'll talk a lot more about fluid balance in the next lecture. Just the basics. Just remember, sodium's on the outside of the cell. In terms of nerve transmission, I know that you guys we've already done this in this class, but I'm sure you started doing this in like high school biology, the whole nerve transmission and action potential thing. So a very brief review. Remember, there's the resting phase at first. So that's when the sodium and potassium channels are closed. So everything's kind of at its kind of normal baseline level. The next is the depolarization phase. So that's when sodium channels open up, and then sodium moves from the outside of the cell through the channel to the inside. Then the third phase is repolarization phase. The sodium channel closes, and then the potassium, which is found in high concentrations on the inside of the cell, moves to the outside. Then there's also the resting phase is restored. That's basically the very last thing where things are kind of shuttled back to where they should be. So the sodium is pumped back to the outside of the cell where it usually is, and then the potassium is pumped back to the inside of the cell. And that's all done by that sodium potassium ATPase pump. So that's the same one that was actually working in the enterocyte to get sodium outside, basically out to the blood. And then if you remember too, it's actually 3 sodiums are exchanged for 2 potassiums with that ATPase pump. And then really it's that whole generation of the action potential that allows that impulse to propagate down the neuron. So that's, it's all these channels are like open and closing, and that's what allows your nerves to kind of transmit, transmit that impulse. So moving on to the third function of sodium, muscle contraction. So sodium helps generate that action potential down a motor neuron as well. So pretty similar to what we saw for general nerve impulse transmission, but this one now is the motor neuron. So that's the neuron attached to the muscle. So the nerve impulse travels down, action potential traveling down the neuron, that's what I'm trying to show you. When the action potential reaches the neuron terminal, remember that causes an influx of calcium. So calcium enters. We also looked at this in the calcium lecture. When calcium enters, that causes the neurotransmitter acetylcholine to be released. The acetylcholine then binds that muscle cell, which generates a new action potential down the muscle cell. And then that causes calcium to be released so that it can participate in muscle contraction. So remember, we talked about it very briefly, but calcium is involved in muscle contraction. And basically it kind of acts like a blocker. So when your muscles contract, it kind of kicks calcium out. So those actin and myosin filaments can overlap. So calcium kind of blocks them from overlapping. So in order for them to contract, it kind of gets kicked out. So that's what I mean by that. All right, so moving on to sodium excretion. In general, all the electrolytes, urine is the primary excretion route. So for sodium, potassium, and chloride. Aldosterone is a really key regulator of electrolyte balance. So aldosterone, just keep in mind, is something that when it's released, it promotes the reabsorption of sodium. So it acts on the kidney and it tells the kidney to basically, while it's filtering all the blood, to not let go of sodium. So bring it back into the body. But then whenever sodium is brought back in the body, it basically also causes the excretion of potassium. So we're going to go over this in the water lecture a lot, kind of more of the mechanism, but just remember, aldosterone reabsorbs sodium, brings it back in, kicks out potassium. So aldosterone, it basically helps your body hold on to sodium and get rid of potassium. It's kind of the main thing I want you to remember at this point. Another way that we can lose kind of most of the electrolytes is by sweating. So that's the secondary excretion route. Most of the time, if you're in kind of like a temperature controlled environment, you're not going to lose a lot by that. But obviously, if you're like in a really hot climate or if you're doing vigorous exercise, you can lose a lot of sodium by those means. Sodium deficiency is called hyponatremia. So I have that, I believe, on the next slide. And deficiency doesn't really occur due to low dietary intake. So it's not like you're not eating enough salt, so then you're going to go deficient. You're going to become deficient. It's mainly all of these electrolytes, you can either get toxicity or deficiency, either because of like profound fluid loss or some type of fluid imbalance leads to toxicity or deficiency. Like your kidneys aren't working properly, but for all of them, it's very rare that any changes in diet intake lead to toxicity or deficiency. So just keep that in mind. So deficiency can occur, I'm just trying to show you, because of kind of excessive sweating, because you're losing a lot of sodium, or excessive water intake. You definitely don't want to consume too much water. There is such thing as water toxicity, because what happens is it dilutes your blood too much, and then your sodium is just too diluted and it can't help out with all those action potentials. It's basically just too far away from those cell membranes to be, yeah, it just gets too diluted and it just can't participate in those action potentials. It's just not like close enough, literally. So symptoms of sodium deficiency are things you probably have maybe experienced mildly before, like muscle cramping. Hopefully you didn't get to the point of nausea or vomiting. But if you ever have, yeah, if you exercise too much sweating, that type of thing, you can start getting muscle cramps because of having, high losses of sodium. So again, deficiency of sodium is called hyponatremia. And to just show you a couple more examples of this. So excessive sweating, this is commonly seen in triathletes. So 4% of Ironman triathletes are treated for hyponatremia after each race. And hyponatremia can generally occur when you lose about 3% of body weight by sweating. So it's almost guaranteed to occur. And that happens in a lot of, it can happen in marathon runners and anybody kind of doing extreme levels of exercise. Excessive vomiting could also disrupt the water to sodium ratio, so that's another thing that can lead to deficiency. And then excessive water intake too. I'll show you on a next slide an example of this, but that also disrupts that water to sodium ratio. Sodium becomes way too diluted in the blood, so it basically can't perform its job in action potentials. And also drinking too much water too fast can be a problem. So I'm not sure, this happened about 10 years ago or so, like 10, 12 years ago, I think. So this is actually a case of someone that died by water intoxication. So when was this? I think it was like 2008 or something like that. Oh yeah, 2009, I guess. Oh no, 2007. There was this radio station that basically held this contest where they said, come into the radio station and drink as much water as you can. So they had like 20 people competing. And whoever could drink tons and tons of water and then hold their pee, so they called it hold your wee for a wee. So if you could hold it and not go to the bathroom, the last person standing basically got this like Wii, like a Nintendo video game console thing. So what happened was somebody, I guess, eventually won this, and then this woman who did not win the video game thing went home and she died. She basically, her sodium to water balance was totally disrupted. So she went home, she was by herself, and went home from the radio station and then just like collapsed and died because of water intoxication. So, and I heard during the actual radio show, there was tons of doctors calling it, being like, you can't do this. Like, people are going to die. This is like a horrible game to have. So if you ever see anyone like chugging tons of water, or if people are like betting each other to do that, I'm always like, oh yeah, you think water is like amazing and it's always like great for you, but in a lot of cases it is, but having excessive water intake over a short period of time can be deadly. So toxicity of sodium, that has not been established as of, to kind of explain this a bit more, there used to be a TUL for sodium up until last March. So about a year ago, in 2019 in March, they actually removed the TUL. they changed it to not established because scientists couldn't really determine the precise UL that would be associated with adverse health effects. So it used to be at 2300, but now it's just not established. So just to point that out. So yeah, there's no TUL for sodium. And then the toxicity of sodium is called hypernatremia. So remember, deficiency is hyponatremia. Toxicity is hypernatremia. So, and that's generally not caused either by high dietary intakes of sodium. It's just that as long as you're drinking enough water, your kidneys can excrete the sodium. It excretes it in about like 30 minutes to an hour. So the second you take in like too much soy sauce or whatever it is, your body will get rid of that almost immediately with, a lot of other nutrients that it doesn't want. But people that are kind of at risk for sodium toxicity are people that can't express thirst properly, or anyone with like a kidney problem as well. But it really happens. There's certain disorders where people just don't ever feel thirsty. So that can actually lead to hypernatremia because they don't have enough water coming in to help like get rid of the salt or get rid of the sodium. Acute toxicity, I don't know exactly when this would happen, but if you consume 5 teaspoons of salt, even if you consume like half a teaspoon of salt in one go, it's like, I don't know if you've ever tried it, but it is disgusting. I think when I was like a teenager in camp, we would like tell each other to like, like dare each other to do this. And I remember having some like small level of it and I felt like I was going to vomit. It's like your body reacts so strongly to it. So yeah, it can lead to nausea, vomiting, and abdominal cramping if you take in like a really high amount really quickly. All right, so moving on to potassium, our next electrolyte. So remember, potassium is the one that is found inside the cell. It's an intracellular cation. So that's the one that, is primarily on the inside, whereas sodium, again, is primarily on the outside. Food sources of potassium, you can find potassium in almost every naturally occurring food. It's in pretty high amounts in fruits and vegetables and dairy, nuts, beans, that type of thing. Processed foods, though, contain very little. So any naturally occurring food will have a pretty good amount. Potassium, if you were interested, so the AIs for that, for males is 3,400, and then for females is 2,600 milligrams per day. So again, males 3,400, females 2,600, and it might help to just write that on this slide. But if you look like just, a serving of a potato, you almost get like 1,000 milligrams. So potatoes are really high amounts. One of the things people always ask, or one of the things they expect you to know as a nutrition person, is how much potassium is in a banana. So here it is. It's 450 milligrams. If anybody quizzes you on that, you can just say, yeah, it's 450. Maybe they'll be impressed by that. I don't know. But yeah, if you just look down, things contain, most of these things will contain anywhere from like 300 to 400 just in one serving of like fruits or vegetables or dairy. So people consume, it's on another slide, but I think people generally consume around 3,000 milligrams of potassium in America per day. So that kind of falls short for men because that their limit or what they need is 3,400. But for women, most women do get enough potassium in their diets. So, and then just to look back at this previous figure that we talked about, so just remember the main thing that kind of disturbs that potassium to sodium ratio is, processing foods. And you're not getting rid of the potassium here. So that potassium's still present. You're just adding so much sodium that it's disrupting the ratio. That's all I'm trying to tell you. But if you're a type of person that consumes very little processed foods, you're probably getting pretty high amounts of potassium and pretty low amounts of sodium. So there is, interestingly, food labeling for potassium. A rich source of potassium is something that has more than 20% of your daily needs per serving. And then a good source has 10 to 19%. But at the same time, I've very rarely seen any labeling for potassium, just because it's always on, the things that are high sources are like fruits and vegetables, and you don't really see like labels on that type of thing. Somebody told me that Whole Foods sometimes labels in their like fruit and vegetable section, but I don't know if I've seen that. Potassium supplements, you think, oh, okay, well, potassium is healthy. It's much healthier than sodium because it's found in fruits and vegetables and non-processed foods. So maybe I should supplement with it, but definitely do not do that. Potassium supplements are actually super dangerous. In fact, most places you can't even find potassium, just like, the Target and Walgreens. It's very rare that it's even on the shelves. It's usually like behind the counter. And that's because it can lead to, if you take in higher amounts, it can lead to cardiac arrest. So if you have any friends or anybody that's taking this regularly, I would definitely tell them to stop. It can also lead to like GI distress, cramping, that type of thing. You should really only take potassium supplements if you're advised to by a doctor or a dietitian. Like somebody has to monitor you doing that. And I'll show you in a little bit, there are some people that need to do that. Like people on blood pressure medications excrete a lot of excess potassium, so they are often supplemented with it. But it's not like vitamin C or one of those things that you should just be like taking, even though you think it'd be good for you because it seems pretty healthy. But yeah, please don't take it, and make sure others that you know are not taking it as well unless they really need it. So again, the AI for males is 3,400 milligrams per day. For females, it's 2,600. And oh yeah, I do say it here. So most Americans consume around 3,000. So women tend to consume enough, males fall short a little bit. So the rationale for the AI is basically something that they notice in studies. If you're consuming this amount of potassium, it may help to kind of keep your blood pressure regulated. But there's been a lot of confounders, whenever you're looking at cholesterol levels and blood pressure, it's not just the amount of potassium in your diet. It's like, do you exercise? Do you have access to healthy foods? Like that type of thing. The DRI was also changed. So I told you that the TUL for sodium was removed. But the thing that they just changed last year for potassium, so I kind of mentioned that down here, it was actually lowered. So these two numbers used to both be 4,700 until last March. And then they lowered it because they realized, people didn't need to take in that much to regulate, to have like adequate levels of blood pressure basically, and no one was consuming this much. Like I've analyzed a lot of food records in my time, and I've never seen anyone, unless they have like really perfect diets, consume that much. So really most people fall around 3,000. Absorption of potassium, pretty simple. It occurs by two main processes. So even though sodium had its own special kind of absorption mechanisms, potassium is very similar to what we saw with water-soluble vitamins. So passive transport is used in cases of higher intakes of potassium, so simple diffusion. And then in terms of lower to moderate intakes, that's when you're using active transport. And it's actually a potassium hydrogen ATPase pump that brings it in. The exact percentage of potassium absorption is not known. Potassium has the same functions as sodium. So remember, it's like fluid balance, nerve transmission, muscle contraction. So once you've kind of memorized what those functions are for sodium, you basically don't have to go any further. It's the exact same things. So there's actually no function slides for potassium. Excretion of potassium is basically, as I mentioned before, mainly in the urine. And so try to remember back, what does aldosterone do? What does it do to sodium? Does it kick it out or reabsorb it? It reabsorbs sodium, and in exchange for that, it excretes potassium. So aldosterone is something that promotes the excretion of potassium. And blood pressure medications tend to increase potassium excretion. So as I mentioned on the supplement slide, these are some of the main people that will be taking, that you might see need potassium supplements, because they have to increase potassium concentrations, just because those blood pressure medications are kind of like kicking out too much potassium. So the deficiency state for potassium is called hypokalemia. And you should definitely know these terms, though they're used pretty frequently in hospitals. So hypokalemia is deficiency of potassium. And again, as I mentioned before with electrolytes, a lot of it, the toxicity and deficiency is not because of diet intake, not because you're not getting enough or consuming too much, just because your kidneys can regulate this stuff pretty well if they function properly. So causes of hypokalemia are kind of similar. It's like vomiting and diarrhea, so profound fluid loss can lead to electrolyte imbalances. Refeeding syndrome, when people are just given too low amounts of potassium, that can lead to deficiency when they're like hospitalized and doing IVs or whatever. And blood pressure medications are one of the main reasons. And a friend of mine's mom was on, like, needed to start blood pressure medications a few years ago. And it was actually, you probably know people on this, there's a ton of people on these meds, but she kept on passing out. Like they just couldn't get, her fluid balance and blood pressure regulated. Like, she was constantly taking potassium. But yeah, it's pretty common. People like kind of just collapse and faint from these things just because their blood pressure gets too low. Symptoms of hypo, so the deficiency, muscle weakness, irritability, sometimes even cardiac arrhythmias. In terms of toxicity, the TUL for that has not been established. Hyperkalemia is the name of the toxicity syndrome. So remember, hypokalemia is deficiency. Hyperkalemia is toxicity of potassium. And that was what I was talking about. You sometimes see this in people that are taking tons and tons of potassium supplements because they think it's good for their blood pressure. But when you take really high amounts, it can lead to cardiac arrhythmias and even cardiac arrest. So actually, like, several people have died from taking potassium supplements. So please don't take them. So who is affected by this kind of like toxicity? It doesn't really, again, develop from high dietary intakes. It really happens in people with renal dysfunction. So people that can't excrete potassium properly. Those are the people that get hyperkalemia. All right, our last one, chloride. This one's pretty short. So just to let you know, we're almost done here. So chloride, most of chloride is in the extracellular fluid, just because the main thing I want you to remember, chloride follows sodium. Water follows sodium, and so does chloride. Sodium's kind of like this leader, where both chloride and water like to follow sodium throughout the body. Same within foods. Wherever you find sodium, you tend to find chloride as well. But so chloride's on the outside of the cell, most of it with sodium. There's small amounts or trace amounts on the inside, but most of it is with sodium on the outside. And then when we consume chloride, we're mainly getting it from table salt intake or processed foods. So, because NaCl, they're combined. And since we're getting like more, like 3/4 of our intake of sodium from processed foods, we're also getting most of that from chloride. That's how we're also getting most of our chloride too. The DRIs for chloride, just to tell you, these are set on a molar equivalent basis to sodium. So for chloride, it's 2300, and that's just because that is what you're already getting when you consume it as table salt. So that's kind of like, again, it's because we're getting it from the same source, table salt usually, and that's how much chloride is present when you're consuming the amount of sodium that you're consuming from table salt. The rationale for the AI is really just, this is the amount of chloride necessary to maintain plasma levels and help with fluid balance. And then in terms of absorption, we absorb about 100% of our chloride, and this occurs by two main transport processes that are sodium related. So the first one is the sodium glucose cotransport system. So the funny thing about chloride is this is basically the slides from sodium. So it's showing you that sodium goes into the enterocyte alongside glucose and eventually gets kind of kicked out with this ATPase. But what chloride likes to do, the minute it sees sodium entering the cell through its kind of proper mechanisms, chloride just sneaks through between the enterocytes in this paracellular absorption mechanism. So it's kind of like, I think we saw that for calcium too. It kind of just sneaks through because it's always trying to follow sodium. So now it's sneaking through and just following sodium into the body too, but it's sneaking between the enterocytes. And then it does the same thing when sodium's absorbed by that sodium channel. So sodium enters, gets kicked out by the ATPase, chloride senses this, and then just follows it in, sneaking in between the cells. So that's how it gets in. It just sneaks in. So functions are very similar to sodium and potassium in terms of fluid balance, since chloride follows sodium. And again, we'll talk about fluid balance a lot in the water lecture, so we'll go into those details. But it does have its own mechanisms, its own things that it does, its own functions. It's a component of HCl, obviously. So we talk about HCl in almost every lecture because it's a key component of digestion. But it also has a role in immunity. So just remember HCl, I know we've talked about it in most of our digestion slides. It's secreted from the parietal cells of the stomach, and it plays a really important role in protein digestion. Remember, it's the one that activates pepsin. It also renders the stomach sterile against pathogens. So in general, that's what it is. And remember, the stomach pH, because of the HCl, hovers around a 2, so it's extremely acidic. The other thing that, another key function of chloride is actually an immunity. So specifically, it helps kind of destroy pathogens. So in phagocytosis, chloride's released by white blood cells. So remember, phagocytosis is when basically, usually macrophages are kind of engulfing, surrounding these critters or whatever kind of pathogen that enters our body. And what happens is the way that the body or the macrophage kind of kills off this pathogen, is that chloride is released from lysosomes in the macrophage. And the chloride literally just breaks apart all the membranes. So that's how it kills it. But it's almost like bleach. Like it kind of, just like melts it away, destroys the membrane. And so that's how we get rid of a lot of like microbial products in our body. For excretion, again, urine is the primary route of excretion. So it's basically regulated. Remember, chloride follows sodium, so it's regulated by the same mechanisms of sodium. So what does aldosterone do to sodium? Aldosterone basically helps sodium get re-enter the body, get reabsorbed. And so aldosterone, just by way of doing that to sodium, since chloride follows sodium, aldosterone also regulates chloride excretion in that same way. So whenever sodium re-enters the body, because aldosterone's acting on the kidney telling it to do so, chloride kind of sneaks in again and just follows sodium back into the body. You can also lose it through sweat, so that's a secondary excretion route, but it's kind of small amounts of chloride are lost by that method. Deficiency of chloride is really rarely reported. I honestly don't think you're really going to see this. It's mainly just because our diets, have high amounts of salt in it anyway. You can get lower plasma chloride levels with profound fluid loss and like vomiting and diarrhea, so the same thing that we saw before. So again, not diet related. You don't get toxicity or deficiency of chloride because of high levels or low levels in your diet. Symptoms of chloride deficiency are convulsions, weakness, irritability, mental disorientation. So a lot of the kind of like non-specific things. It does not have one of those names like hypokalemia or hyperkalemia. It's just called a deficiency of chloride from my understanding. In terms of toxicity, there's not really anything that's been reported for this. It's just like masked by whatever happens with sodium because they're always kind of present together. Obviously, You can see maybe toxicity symptoms in salt-sensitive individuals, that taking in like higher amounts of table salt can increase blood pressure, but that's like the only thing. And then they set the TUL based on its molar equivalent, again, to sodium. So it's 3,600 milligrams per day. I made a mistake on this slide. This is the old, basically the old number for chloride, or sorry, for sodium. So you can kind of just scratch those out. Oh no, sorry, you know what? I made a mistake here. That should be 2,300. I thought I didn't correct it just because there's been so many changes to the electrolytes. So scratch out 1,500, keep 2,300, because 2,300 is the normal intake, or if you go back to the DRI slides for chloride, 23 is correct. All right, so let's do kind of a quick review here. If you remember phosphorus and magnesium, I think we can do this another time. Calcium, most people kind of know what that does. So phosphorus and magnesium food sources. You would think because it's a P that it might be plants, but it's the opposite. Phosphorus is meats. Magnesium with an M is actually plant products. So meat and then plant products. What are the functions of these two? What do they do? Well, if you remember, these three are all involved in bone metabolism, or bone mineralization, I should say. So they're all vital components of bone. And then another thing that both of them do is phosphorus is obviously in ATP, and then magnesium helps stabilize it. So they're kind of similar there. Deficiency and toxicity, is there any disorders for those? Is there like a specific disorder? No. So basically it's, pretty rare. And then sodium, so the electrolytes now, where do we get sodium from? Table salt, processed foods. Where do we get chloride from? Same thing as sodium, table salt, processed foods. Where do we kind of eat high levels of potassium? So that would be non-processed foods, vegetables, dairy, nuts, anything like that. So all three of these, in terms of function, are involved in fluid balance. And then the other thing to remember, what are some other things other than fluid balance that sodium and potassium are involved in? Where did you see sodium and potassium before you took this class in your physiology classes? So that would be nerve conduction and muscle. So that's where with the whole action potential thing. And then what's another two functions of chloride? What does it do beside fluid balance? What did we just talk about? So it's involved in immunity. Remember, it helps to kind of like melt pathogens. And then it's also involved in, what's the other one? HCl. So those are the two things that it does. What are the deficiency terms for sodium, or deficiency and toxicity? So that's hyponatremia, hypernatremia. What are the ones for potassium? Hypokalemia, hyperkalemia. Chloride doesn't really have any toxicity or deficiency, but the main point I want to make here is usually the main way that you get kind of toxicity or deficiency is just from problems with fluid balance. So either your kidneys aren't working properly, excessive vomiting, sweating, that type of thing. You're not going to get high toxicity or deficiencies of any of the electrolytes because you eat too much of them or because you eat not enough of them. So those are all just because the body is having problems regulating kind of like water and fluid balance that you would then kind of, or problems excreting them, that type of thing. So yeah, just remember that. But yeah, for chloride, yeah, nothing really. It's either rare or unknown. All right, great. Well, I hope you guys have a great rest of your day, and I'll try to post the water lecture soon.